The NES can tell a game when a note ends. Test ROMs use this. Games don't care. Most games don't do anything when a channel's length counter ends. It's mostly useful to measure instruction lengths in test ROMs. I move the APU to its own file. I grab the table of note lengths and frame counter ticks. I planned ahead for variable screen width. I added length counter registers to the machine state. These registers needed to be initialized at reset. I made PSG channel count not a magic number. PSG, or Programmable Sound Generator, means pulse, triangle, and noise. These channels play simple formulas, not arbitrary sampled waveforms. I built a way for the CPU to end a note, otherwise the note's length counts down. When a channel's hold note flag is on, its length counter stops. I reflected the end of a note back to the CPU. Hindsight, the way I did this wouldn't allow consecutive notes. Note to self, tick length counter and pulse sweep at the same time. I added names for the channels. I started making the changes compile when I realized I'd need a function to set a note length. I called this function from each channel's register addresses. I continued documenting the other thing that the frame counter touches. Sometimes I feel a need to spill everything I know onto the page before my mind wanders. I started reading up on the sample channel. Writing to APU status acknowledges the end of sample interrupt. So does turning off the interrupt. I added a few more sample playback registers. I checked the log of writing to APU status. Let's see when it expired. It passed Blarg's instruction timing test. What else could I do today? I stopped all PSG channels on reset and looked for other things to initialize. I copied the pitch lookup tables for noise and sample playback and divided them by 2 to fit the get and put cycles. I added variables for the sample channel state and drafted pseudocode for the sample reader. This let me write a function to start playback. That was enough for the day. The first sound I added was timed writing to the DAC, like in Big Bird's Hide and Speak. Then I could make sample playback also write to the DAC. Some NES emulators for handhelds can't run Big Bird because they don't support writing to the DAC. I made the DAC a writable register and had the SDL front end gather that as its output. I made the changes from late yesterday compile.
Hello.
One of my earliest sample playback tests worked. Crowd by Kragan is a byte beat composition. It's a one-line formula that takes a time and returns a sample value at 8,000 Hz. Most of the MD Fourier tone generator doesn't work yet, but there are a few clicks. An equalizer test ROM makes pink noise and a sine sweep.
Make your selection now.
My approach of playing samples first is sort of back to front. I started a delta modulated sample. Delta modulation moves the output one step up or down each sample. Games use it for drums, bass, and voices. I move the remaining steps of pseudocode into TIG APU. I added what it does on each sample and when counting down to the next sample. Each byte contains 8 differences, 1 in each bit. If the bit is 1, the value increases by 2 unless at maximum. If the bit is 0, the value decreases by 2 unless at minimum. Once it has played all samples in a byte, there either are more bytes or there aren't. If there's something in the 1 byte prefetch buffer, move it into the sample shifter. At the end of the wave, if looping is on, play the wave again. Otherwise, signal that the wave has ended, and insert an interrupt if that's enabled. I made all this sketch compile. Some of it was running. I needed to read samples from memory. That would require understanding how DMA actually works. The CPU would be responsible for reading samples under the DMA unit. I started translating the description on the wiki into C. Making OAM DMA and audio DMA work together would be complicated. It started to click. Each of the OAM DMA steps was the same. If not halted, wait for a read to halt the CPU. Then wait while the current cycle is a put. Then read on a get cycle and write on a put cycle. Audio DMA waits for a read, waits one more cycle, waits while in a put cycle, and reads a byte of samples. Someone added a bunch of worked examples for me to study. That was a lot to absorb. By then, I had an idea of what was going on with DMA. Two DMA units share a single mechanism to halt the CPU. All games use OAM DMA to copy a sprite display list from RAM to the PPU. Some games use DMC DMA to play sampled sound from ROM in the background. I renamed machine struct fields to reflect the new understanding. I updated how OAM DMA gets started. I started rewriting the DMA state machine. The CPU halts if either DMA unit requests it. That means either OAM DMA in progress or DMC DMA with positive length and empty prefetcher. It takes one read cycle to halt the 6502 CPU core. I moved the DMA state machine to its own function for readability. The function takes the address requested by the CPU because it rereads that address several times during DMA. DMC DMA has priority over OAM DMA so that the sound doesn't hiccup while it copies sprite positions. Otherwise, sampled sound would have Genesis laryngitis. For some reason, DMC DMA waits one more cycle before waiting for get. The sample byte read from memory goes into the playback register, and the pointer moves to the next byte of compressed samples. When the length runs out, it can loop or interrupt if set so. That's part of the data reader, not playback as I had guessed. When the sample runs out of data, it stops playing for 8-bit periods. I factored out waiting for get, which both DMA units use. Then I rewrote OAM DMA into this framework. I made the new DMA implementation compile. I reran OAM DMA tests to find regressions. RHDE 240p test suite and Haunted was still working. I ran MD Fourier to see what sample playback would do. I needed a test ROM that took less time to start playing.
Hello.
Goodbye. I needed more logging. It was reading the wrong bit of APU control to start playback. Still not playing. I added a way to set the wave start address and length and logged every sample byte fetch as well as the program counter when a sample starts. I looked up what the status register is supposed to be doing. Almost there. I added a way to set the sample rate. That was it. Bonus tip for Firefox users. After you've closed a bunch of tabs, sometimes the browser doesn't immediately return memory to the operating system. Some memory is used to make Ctrl-T to launch a new tab faster or make Alt-Left to go back to the previous page faster. Visit About Memory and choose Minimize Memory Usage every so often. I was itching to make a test ROM for disabling SRAM in MMC1, but I had an emulator to make first. Like the dots the PPU produces, the output of the sound circuit is part of the machine's overall output, so I figured I'd collect this as part of the machine struct so that front ends could send it wherever they need. SDL could send it to the speaker and Headless could write a WAV file. It took me a while to figure out how much sound to store. I had planned to emulate sound at half the CPU clock rate, seeing as that's when pulse noise and most samples change, and the aliasing from triangle wouldn't be horrible. I added a sample array and a fill level to the struct. I grouped what audio things run on put. The 5 channels aren't mixed evenly. The sample channel makes triangle and noise quieter, and games use this. At first, I used the wiki's rough linear approximation. I estimated how much headroom I'd need in the output. I gave a place for the mixer to store the output. To limit action at a distance, I had the CPU append the mixer's output to the buffer. Notice I made a mistake here. Only read cycles are writing output, not write cycles. I had the SDL front end decimate samples from the mix buffer, which I cleared on reset. Reading the mix buffer later let me remove 2 copies of sound logic. Decimation is a quick yet aliasing prone method of downsampling. I made it compile and tried it on my sample test.
Hello.
The buffer was working, so I got rid of a bit of logging, but that was only the beginning. Next I wanted to add sound logging to the Headless front end. I didn't need to pander to common sound cards in Headless because a WAV file could have any sample rate I wanted. Ideally, one that evenly divides the CPU clock. A rate of 52,500 Hz is close to a nice divider. I looked up how to write a RIF WAV file. I expected it to be about as complicated as Windows bitmap. As with ping, RIF WAV has a bunch of optional chunks. At least there aren't any checksums that I'd have to calculate. The so-called canonical wave has a fixed length header with only the required chunks followed by data. I added it to my file format notes document. Programs that record to disk need to guess the length, write that to the header, and adjust the length after recording. There aren't a lot of tests for MMC1 SRAM disabling. I was slowly getting frustrated with inability to test my code. I spent a few days of Epiphany Tide designing my own test ROM. Leave a comment if you want to see me make this.